we expanded our view of Burrows-Wheeler order so that it pertains not just to strings, but to simple graphs that are straight line graphs. Here we want to expand that notion of Burrows-Wheeler order to more complicated graphs that aren't necessarily a straight line. And remember when we talked about the graph nature of the graph version of the Burrows-Wheeler transform, we had these nodes that we labeled according to rows of the Burrows-Wheeler matrix. And we said there were basically two different ways we could think about these nodes. They have kind of a way of thinking of what's incoming on that node and a way of thinking of what's spelled out on the path leading from that node. If you take the nodes in Burrows-Wheeler order and ask what's the character labeling the incoming edge for each node, we said that's the Burrows-Wheeler transform. That's because the node labels are based on alphabetical order, and looking at the label of the incoming edge is like looking in the last column. You know, it's like rotationally going to the left is like going around to the last column where the Burrows-Wheeler transform is. And then we said the other nature, the sort of outgoing nature, is if we start at a node and follow the chain of links, let's say we follow that chain until we see an edge labeled with $, and then we stop, what we end up spelling out is a suffix of the text, and putting the Burrows-Wheeler order on the nodes means that we've got those suffixes in alphabetical order. Okay, so now we want to ask the question, do these two natures still straightforwardly hold when we have a graph that's a little bit more complicated, like this one? All right, so again, those two natures. Can we talk about nodes in terms of the label of their incoming edge? And can we talk about nodes in terms of the strings labeling the paths that are outgoing from those nodes? So in short, the answer is going to turn out to be no. And one of the two problems that we have is pretty obvious, right? Let's just look at this node right here. This node has more than one incoming edge. So what does it mean to say that the node is can be viewed in terms of the label of its incoming edge? Now there's two of them. So that is going to be a problem. So nodes that can have multiple predecessors, right, in this more general graph, a node can definitely have more than one predecessor. It can have more than one successor as well. The other problem is the other nature being what's the string that's spelled out as we follow the path of outgoing edges. That's still pretty straightforward for several of these nodes, right? So for example, starting at this node here, even though it's in this diamond, in this sort of bubble shape here, if we start at this node and follow edges, we see one string, $CAT$. That's straightforward. However, if we start in this node or any of the nodes upstream of that node, we have a choice. We can either go this way or go this way. And it means that there's not just one string spelled out along the path going from that node to the $. Okay? So both of these facts are going to mess up our notion of how we thought about the nodes before. But maybe we can still save ourselves. All right, so the question that we'll start with is, can we salvage some notion of Burrows-Wheeler order, even though the way we would like to establish that order is by putting these outgoing labels in alphabetical order? The fact that these have more than one possible string going out from them is a problem, but maybe it's a solvable problem. So let's look at it a little bit more closely. Okay, so what would be great is if it turned out that even though some of the nodes had more than one string that could be spelled out along a path from that node to the $, if it turned out that nonetheless there was still a total order over the nodes that we could easily define, something like Burrows-Wheeler order. Well, let's see if this is the case. So again, some of these nodes are pretty straightforward in terms of the labels of the outgoing edges going to the right until we get to the $. For example, for this node, it's just $. For this node, we've got $T$. For this node, we've got $AT$. So far so good. For each of those nodes, if you label them according to what's the string that gets spelled out as you go to the right and stop at the $, there's clearly a total order over all these strings, right? Two of them are the same length, right? $CAT$ and $GAT$, but it's fine. There's going to be, you can take all these and put them in order. Here's the first one, second one, third one, fourth one, fifth one. No problem. So some of these nodes are more complex because there's more than one string that can be spelled out going to the right. So this node right here, for example, if we go up, we get ACAT $. And if we go down, we get AGAT $. So you can think of the label for this node as being sort of like the set containing both those strings, right? Those are both possibilities. Okay. So let's label it that way, and let's label the rest of them similarly. So like, for example, the label for this node will be just like the label for the node after it, except we're going to prepend a T. So T, ACAT $, and T, AGAT $. Okay, and so on. So here we go. Here's our labels for all the nodes. It's a little bit more complicated than before because for these nodes to the left of the diamond, they need to have more than one string in this label. Okay, now let's say we wanted to put all the nodes in order, alphabetically, just like we did when we had a straight line graph and we're considering just a string. Okay, so I'll tell you what's easy is what should be the node that gets the first, that goes in the first row, right, that gets the lowest index. It should be this one, right, the one that has $sign right after it. Okay, that's because $sign is alphabetically less than all the others, and none of the others can possibly start with $sign. So that one's easy. Now let's look a little bit closer and think of which one comes next. What seems clear is that whatever's going to come next is going to start with A, right? So let's just highlight the nodes whose labels start with A and leave the rest kind of grayed out a little bit so it's easier to see. Okay, so the nodes in question are this one, and this one. And so my next question is, even though these nodes have more than one string in their label, is it possible that we can actually figure out their alphabetical order unambiguously? In other words, we're pretty much okay as long as there's no sort of overlap between the intervals of the alphabet defined by the first and second strings. Okay? So in this example, it's actually the case that this candidate down here, ACAT $, AGAT $, that's clearly alphabetically before either of these two, right? Both of these two are alphabetically before either of these two, and alphabetically before this. So it seems pretty clear that we can put a 1 here, okay? That one's next. And then as we compare these two, right, it's pretty clear that this one comes alphabetically before either of those. So that one should be next. That one gets the 2, and then this one gets the 3. So there was no ambiguity. It was clear how we had to assign 1, 2, and 3 in that case. And let's keep going. So let's take the strings that start with C and the strings that start with G. Here they are. And then let's ask ourselves, is there any ambiguity? Well, clearly CAT $ comes next, right, because the others start with G. So let's give CAT $ the 4. And now let's look at GAT $ versus these. Well, clearly GAT $ comes next because that comes before both of these, right? So let's give that a 5, and that is 6. Okay? All right, now let's do the ones that start with T. Okay, so what comes next? Okay, so T $ is going to come next. That clearly comes before either of these and either of these. So let's give it a 7. And what comes next? Well, we've got TAC and TAG. Those both clearly come before either of these, which start with TTA. So that one's next. Let's give that an 8 and then a 9. And we're done. And look what we did. We gave the nodes of the graph labels so that they are in a total order and there's no ambiguity. In other words, the fact that some of these nodes had more than one string that could be spelled out as we moved toward the $sign didn't interfere, in this case, with the fact that you could with putting the nodes in order. There was still an alphabetical total order. What changed was, instead of that being a total order over individual strings, the total order had to be inclusive of these sort of like ranges or intervals of string space. It had to be the case that these intervals didn't overlap each other so that we could still put them in a total order. So that's pretty cool. The graph still has something like a Burrows-Wheeler order. And so as a consequence of this, we'll have more to say about this property, but as a consequence of that, we can still do matching, right? We can run our matching process where we are trying to find the paths whose edge labels correspond to our query pattern and match successively longer suffixes of our query pattern. And we still have our consecutivity property. In other words, if we look at the heads of all the paths of all the that match our query so far, we'll see that they have labels that are consecutive. So for example, let's say we're matching AGA against this now graph. It's a graph, and it includes basically two strings. But we can match our query against both at the same time. All right, so let's take the first suffix of just A. I'm highlighting all the edges that are labeled A. And then if you look at the heads of those paths, you can see, interestingly, two of them have the same head, okay? But it's labeled 1, and then this one has labeled 2, and then this one has labeled 3, so they're consecutive. So consecutivity is still holding, at least for this example. If we keep going and take the suffix GA, okay, now there's just two paths that are labeled GA, right here and right here, but we still have consecutivity, 5 and 6. And now if we look at AGA, there's only one path left, so we trivially have consecutivity. But the fact that we could still assign a Burrows-Wheeler order to the nodes of this graph is what helped us retain the fact that we have consecutivity, which gives us hope that we can do FM index-like matching, but on a graph. Okay, so before we go any farther, we want to see if this was just a coincidence or if every graph is going to have this property. So let's just look at one more graph and ask, does it work for this graph too? Well, does what work? Well, I guess the whole being able to give an order to all the nodes thing. The nodes have to have a total order, which again means that for every string label that we can give to these nodes, including these nodes over here, which are going to get a set of strings as their label, is it's still the case that we can put them in an unambiguous alphabetical order. And this graph is just like the one we were just working with, except I changed that character. I changed it from a G to a T. So I made a very small change. So maybe you can feel what's coming, right? Making a small change in order for this to be a profound example, that must mean that I broke the property. So let's see if I really broke the property. So again, it's pretty straightforward what's going on over here in terms of the labels of these nodes, right? There's no ambiguity over here, right? And we got CAT dollar, oops. And TAT dollar. And so far, so ordered, right? These are all in a total order with each other. No big deal. Okay. Now we've got to go backwards and fill in the labels for all these nodes that come to the left of the diamond. And I'll just do this one by hand, just as a reminder of what we have to do, right? We have to spell out this string and we have to spell out this string. And they're just both going to go into the label as two strings in a set. AT dollar, etc. If I do this for all the nodes, I get this. And so again, let's try to give it an order. And again, the easiest node is the one just upstream of the dollar sign, that gets 0. And let's again focus just on the nodes that have strings labeling them where the strings start with A, so that's these nodes. And now let's think, what should come first? Well, this one has an ACAT dollar string in its group and an ATAT dollar string in its group. And so can we say that this, since it has something that starts with AC, and these all start with AT, can we say that this one comes first? Well, let's compare this and this. Can we say this comes first? Well, that's not really possible, right? Because AT dollar sign alphabetically comes after ACAT dollar, clearly, but it comes before ATAT dollar, okay? A is greater than dollar sign in our alphabet. So this actually comes in the middle. And that's a problem, because it means we don't know their relative order, right? One of them's like, it's like, what's the relative order of an interval and a point in the middle of the interval? You know, we no longer are in partial order land. We're in sort of like, in total order land. Now we're sort of in partial order land. So that AT dollar is sandwiched between the two labels that we have for this node. There's no total order. There's no way to put labels on the nodes of this graph so that we have something like a Burrows-Wheeler order. There's no corresponding way of assembling, you know, sort of like the Burrows-Wheeler matrix, because we can't actually put the rotations or the suffixes in order. Okay, so this is bad news, right? It means there's at least one type of graph, and this is a pretty simple graph. And the only difference between this graph and the one where it worked just fine is that I changed the label of one of the edges. Kind of unsettling, right? We don't, how could we predict that this would have happened? Well, before we talk about that, which in the next video we'll talk through the definition of a Wheeler graph, and that's when all these sort of dividing lines will become a bit more obvious. Let's ask the question, can we fix it? Can we just take this graph and change it a little bit and get a graph for which there is a total order over the nodes? Well, here's one suggestion. We're just going to take this diamond, which is sort of almost like a partially unzipped part of the graph, you can think of it, and we're just going to unzip it sort of one more step. So we'll break apart, we'll basically take this node and break it into two, like this, right? So now here's that node broken into two, right? This node became two nodes, okay? But we still spell out the same two strings along that top path and along the bottom path. So if we're using this graph to represent those two strings, we haven't changed what the two strings are, right? So that in some sense, this is a equivalent or equivalently useful graph, but we changed its shape a little bit. And now let's ask the question, did we fix anything? Well, I'll give you the short version, which is we haven't fixed it. And I'll show you where the sandwiching effect is now concentrated. So here's a node whose label is TAT dollar sign, unambiguous. And now let's go back to this node here and think about what its labels are. So that top path is going to be, let's see, TAC AT dollar sign. AC AT dollar sign. And then on the bottom it's TAT AT dollar sign. And TAT dollar sign, so let's do TAT dollar sign and compare it to TATA, right? So this string is actually sandwiched in the middle. It's between these two strings, alphabetically. So we are still sandwiched. So this didn't fix it. Okay, but out of a sense of optimism, let's just try it again. Let's do one more unzip, going backwards. So again, we started out with this node and then we sort of pulled it apart so that now this is two nodes. And now, long story short, it works. We really now are back to having a total order over all the nodes, even though we still have these nodes back here that have an ambiguous label or that have a label that's going to be a set with two strings in it. Still, we have managed to solve the problem. There's now a total order over the labels of all those nodes that includes these nodes that have more than one string label. Okay, so success. And you can sort of see why this kind of graph manipulation was helping, because after all, one of the things that we were doing as we were unzipping backwards was we were reducing the number of nodes that had ambiguous labels, right? Because as we were unzipping, all these nodes now have single string labels, right? I guess more specifically, these nodes now have single string labels. These nodes now have single string labels. it's only these nodes now that have more than one string in their label. And the more we reduce the number of nodes that have that have multi-string labels, the easier it's going to be to actually get a total order at the end of the day. Okay. So what we've learned is that there are some graphs for which we can find this total order. Okay, this basically Burrows-Wheeler order over the nodes. There's other graphs for which we cannot, but we can fix them sometimes. Okay, which is interesting. But we sure do wish, well, we could wish for many things, and actually that's what the next slide is about. What do we want to know? We want to know, well, what is the definition of which graphs this actually will work for? What are the graphs for which we can find something like a Burrows-Wheeler order so that we can have something like our consecutivity property, so that we can do something like string matching like we were able to do with the FM index when we had a simple string as our text. So which graphs does it work for? Do we have the consecutivity property as needed by matching? For matching like we did in the FM index. And then, mechanically, how do we actually represent and query that graph? This is all just a game unless we can actually take that graph and index it, and then query that index structure so as to perform matching in a way that's, roughly speaking, not much less efficient than what we were doing with strings. So that's what's coming up.